Hello everybody, welcome to this new video that explains one of the examples that you find in the GitHub with examples for the course. In this example, I want to show you a possible implementation of a class that perform fixed point iteration. What is a fixed point iteration? Often you want to find the fixed point of a function phi that may be either a scalar or a vector function. That is the point for which x is equal phi of x. And to do that, a simple technique is to start from a given point and then repeatedly compute a new iterate just by saying phi xk is equal phi k plus 1. Sorry, this hat should not be there, and also this hat should not be there. And then you stop when the distance between two iterates is less a given tolerance. This is a standard fixed point iteration. Another possibility, that is the one that I'm considering here, is to do something a little bit more complex. Still, you have an initial point that you have to give, but then when you construct the new iterate, you use, of course, your iterator function phi, but you have possibly an accelerator that is something that tries to accelerate the convergence. Okay? There are several types of accelerators in the literature. I have only implemented one, just to try how it works. One thing, I wanted phi to be rather general. That is, I want this xk to be defined by any things that looks like a vector. That is either a standard vector or an eigenvector. The only thing that I require is that you have the addressing operator, that is the square bracket operator, just to understand each other, and that it has the method size. So I want phi to be able to work. I can decide either with standard vector or with eigenvector. Of course, I could have also considered the case of a scalar phi. I haven't done it. I leave it that to you. If somebody wants to extend also for scalar phi, it's not difficult, as you will see in the following explanation. You could do it rather easily. So let's have a look at the code and how it is organized. The code in the directory src of the example and is called, just with no great fantasy, FixedPointSolver. In FixedPointSolver, let's do a make clean just to make it clearer. You don't have much stuff. You have a README file that explains more or less what I said so far, and a class called FixedPointTrait, sorry, a file called FixedPointTraits, a file called accelerators, and a file called FixedPointIterator. The class FixedPointTraits that is contained here contains the definition of the types, or the main types I want to use in my code. The trait techniques is quite used in generic programming, and is very useful, in fact, because you want to enucleate into a class, typically a struct, because everything is normally public, all the main types, the definition of all the main types that are you going to use in your code. The main types I'm going to use in this code are the argument type, that is the type in which express the argument x, the return type, that is the return type of my function, of my iterator function, that of course must be equal to argument type, since phi must be a function from Rn to Rn, there is no way. And then, very importantly, the iterator function, that is how I want to express phi. And I decided that I will wrap phi inside a standard function, a function of the standard library that takes argument const reference as parameter and returns a return type. Why is the traits are useful? They're useful for many reasons. The first reason is that if you enucleate all the major type in a place, it is easier if you want to change some later on some of the main types of your program just by changing the trait. Okay. That probably is not enough. You will have sometimes to change something else, but in general, but at least for what concerns the types, you just have to change them here. Then you can give the types significant names that help people reading your code and yourself understanding what you're doing. But traits are also useful for selecting different types according to your choice. And exactly is what I'm doing here. I want to be able to give the user the possibility of using either vector of the standard library as argument and return type for my phi, or the eigen vector. This is a vector, in fact, even if it's called matrix, because it has only one column. Okay? So, to give the user the possibility of choosing when he or she writes a program whether he wants to use vectors or eigenvectors, I decided to create an enumerator. Remember that an enumerator is just morally an integer, even if C++11, since C++11 we have this enum class that allows to have a better control on the enumerators. And this enumerator is called FixedPoint argument type and take to value either vector or eigen. If I want a specialization also for scalar, I will add also scalar. Then I have a template that is the primary template for my trait, and that is just an empty structure. This is needed because, remember, I will do then specialization, but you can do specialization only if the primary template is visible. So you need to have the primary template. And the primary template is fixed point traits that takes just one template argument, that is the fixed point argument type, either vector or eigen, and is an empty class. Okay? So what matters? The one that we're going to use, in fact, is not the primary templates, but are its specialization. And there are two specializations. One is for vector, and one is for eigen. So the specialization that takes a fixed argument type vector will have as argument type the vector type equal as the return type, and this iterator function. If instead you choose eigen, well, you will use this specialization, and the argument type will be a vector of the eigen, the return type again, and the iterator function will take as argument and return the vector of the eigen. So let's see how traits are used. They can be used in different ways, and in different examples we will see different ways of using them, but let's see how I've used it in this particular example. So let's go to accelerator. Accelerator implements the accelerators. And I have two accelerators. One is called no acceleration because indeed it does nothing. It will implement the standard fixed point iteration. And the other is, is called, is a type of second accelerator. It's not important here to know what they are. I'm not going to give the technical detail of the code, okay? Remember, there are two accelerators. One that does nothing, it doesn't accelerate anything, and the other one that indeed does some acceleration according to a certain procedure. Let's see the no accelerator. It takes, is a template, is a class template that takes one parameter And the parameter is fixed argument, is a fixed point argument type. So it can be either vector or eigen, right? And as you see, inside this class, I'm using some types, the argument type, iterator function, that are grabbed from the trait. So I'm sure that in all components that I'm using here, I will be always consistent with the type, because the type are defined in the trait. So here I'm getting the right trait specialization, and the argument type and the iterator function type is extracted from the trait. I remember this ugly type name keyword is necessary because these argument type and iterator function are types, but they are template parameter dependent types, because arg is a template parameter. So you have to tell the compiler that indeed these are types. Otherwise, the compiler has no way to know it. So you have to tell it, to tell him, or to tell it by the keyword type name. Okay. If you don't put the keyword type name, it's a compilation error, but likely all good compilers give you a clear warning. They will tell you, aren't sure you want to put type name here, and then you go and correct. So the accelerator has got all accelerator has got a constructor that takes the iterator function, because the accelerator needs the iterator function to work. And here, it will just store it in a variable, okay? So I have here a reference to the iterator function. I'm storing it as a reference. This is not so common. Maybe you haven't seen it quite often. It's a const reference because I'm just using it. I'm not going to write on the iterator function, so I'm using it only at the right-hand side of an assignment, so I'm not going to change it. Normally, you don't use references when you define member variables, but here it is convenient just to save some memory, because indeed an acceleration cannot exist without an iterator function. An accelerator is very linked to an iterator function. You cannot think of an accelerator without the iterator function to work on. So it is convenient just to pass the iterator function in the constructor and put it as a reference. Remember that a reference has always to refer to a value. So you need the constructor that gives the iterator function. That also means that this class is not copy constructible and is not default constructible, because it hasn't got, it is copy constructible, but it's not a default constructible, because it has no default constructor. Cannot have the default constructor because I need to bound this reference to something. So I have to give the iterator function so that the reference can bind to the iterator function that it binds here. Here, the const reference to iterator function mi is bound to what I'm passing with the constructor. So the accelerator has got a copy, actually has got a reference of the iterator function. And it has got a call operator. That is the way I will use the accelerator. And here, since it is no accelerator, it calls the iterator function on the argument. So it just do phi of xk and returns what it will be xk plus 1. Okay? I have a reset, is just a function that I put here is empty for the no accelerator, is needed for the other accelerator, because the other accelerator instead will have a state to perform the accelerator. They need to store something inside, and the reset is just to reset the state to the original state, okay? But here it does nothing because there is no need of resetting anything in the no acceleration class. And then return the identifier for accelerator just if I want to interrogate the accelerator, but it's not very important. This is really not important. There is an identifier so that I know that this accelerator is indeed a no acceleration. But as I told you, this is not so crucial. Then I will leave this is very technical, to implement the other accelerator, and since I want my phi to operate only on standard vector, not only on eigen type of vectors, I had to redefine a few things, how to do the dot product between two vectors, how to do the square norm of two vectors, but it's not so important. These are just internals, are just things that I'm gonna use in the other accelerator. That is an interesting one. I'm not gonna give the details on how it works, so you can find it in the reference, in any good reference. The reference is here, if you are interested. The only thing that here I have is a bit more complicated, because now the reset does something. We'll reset these two variables, length and first time, and the operator, the call operator, is a bit more complex. Note that here, since the operator is long, you see, it's rather long, I didn't define it in class. While here, this is an in-class definition. For the operator, for the call operator, this is just a definition. Okay. This is just a declaration. So this is just a declaration of the operator. And I'm doing the definition out of class because in this way I don't have a very big, I like to have the definition of the class short, so that I can look what is inside the class and not be distracted by a very long method. Even if it is defined out of class, it is still in the header file because it is a template method. Okay, so it has to be in the header file, even if it is defined outside the class. This is different than ordinary methods. Okay, this depends from the template arg, since it is a method of a class template, so it has to be defined in the header file. So this is accelerator. Let's have a look now at the main class, that is a fixed point iterator. Fixed point iteration. I have introduced this flag. If you compile with -d verbose, you find all the instruction in the README file. You get some more thing on the terminal. You can check how the iteration goes. So the fixed point needs some options. The max number of iteration, because I want to be sure that my code ends. So you, in every iterative procedure, always fix a maximum number of iteration, because if your method does not converge, if you don't fix a maximum number of iteration, it will run forever until you stop it with a Control-C from your terminal or with kill or something else. Okay. So I have a maximum number of iteration, and this is the default value. I can change it. This is just a simple struct. I can change this value, but the default is 100, and I have the tolerance when I want to stop my iteration. And the tolerance is fixed to 10 minus 8 by default. So here, this is a bit more complicated. I made it more complicated than necessary, but just to show you that my fixed point iterator class is still a class template, takes a fixed point argument type arg, and takes an accelerator, our second template argument. And this second template argument is itself a template. So I impose by this construct, that is, maybe you have never seen it before, I'm imposing that accelerator, so the second template parameter is not just a type, but is an instance of a template that takes one argument. And the argument it takes is a fixed point argument type. Okay? And by default, the type is no accelerator. No accelerator or fixed point argument type. Okay? And here I'm saying that the argument type is fixed point trait arg argument type. So I get again the type of the argument from the trait. The accelerator type is accelerator arg. Okay? So I'm sure now that the accelerator is using exactly the same types as my fixed point iterator, because it is an instance of a class accelerator with the same argument as fixed point iteration. So it will have the same type, the same argument type, the same iterator function type. So see, here you see how traits are useful. You're making sure that all the components that makes up your code have a consistent types. Then here I will skip a little bit here. This is I make a constructor that takes the iterator function and optionally the conversion option, and I've used this strange constructor just to show you it once. This is a template constructor. So this is a constructor of fixed point iteration that has got a template. And that takes as a first argument an R value reference to the template parameter. What does it mean? It means that when phi is my iterator function. Phi is where I store my iterator function. Okay? And unfortunately here I didn't follow the rule of putting method outside the class, and so things are getting more. Okay, here it is. Iterator function is here, so I have an iterator function, and here the iterator function is initialized with this very strange construct. This means that if the iterator function is something that can be moved and not copied, it will be moved into phi. If instead is something that cannot be moved, it will be copied in just one instruction, std forward if ifun. I'm able to move if I cannot move, if I can move, and to copy if I cannot move. Okay? Then options are initialized with options, and options has got a default that is just constructing a fixed point options. In fixed point option I have fixed the default, so options by default is just an object constructed with the default constructor of fixed point options, so it will contain the defaults. And then I just initialize accelerator that is just an accelerator. I have also a default constructor, just set the accelerator. And I have a getter for the options. This is if somebody wants to. But what is important is not the getter for the option, but the setter for the options. So I can change the option. So I can change the tolerance if I want using set option. And I can set or change the iterator function if I want. And I can also get the accelerator if I want. But these are optional stuff, okay? They're not, the core is a method compute. Here I didn't use the call operator. I used a method with a name that takes an argument type and does all the stuff. In a next version, I will put here only the declaration and the definition out of class because it's a bit too long to stay here. But here I need to check if the distance between two successive iteration are smaller than the tolerance. So I need to set the current distance. And initially, I set it to the biggest double number that it exists. So I'm sure that at the beginning, current distance is surely greater than the tolerance, whatever tolerance I've chosen. Then I need to store the current and the previous iteration that are initialized with x0. And here is an example of a while loop. So until this condition are satisfied, I will continue iterate. What are those conditions? That the iterator counter that is initially set to 0 is less than the max iteration prescribed in option, and that the current distance is greater than the tolerance prescribed in option. And I will then iterate just by compute the current value by calling accelerator, by calling the call operator of accelerator on the previous value. I will call the distance, and then I will set the previous equal to the current, and I adjourn the iteration. If I set this verbose macro, at every iteration I have on the screen the iteration number and the values stored in the current value. If not, I will continue. At the end, I will reset the accelerator so that I can reuse it. And I return a tuple that contains the current iterator, the last iteration, the iteration number, so the last iteration number, the current distance, so the last distance between two consecutive iterations, and this Boolean that is true only if I have converged, right? If the last iteration is less than the max iteration I have prescribed, it means that I have converged in the given number of maximal in the given maximal number of iterations. That's it. Well, distance is just computing the distance. Okay. Just by iterating and computing the two norm of previous minus current. That's it. Let's see how I can use this function, main fixed point. You see, the usage is quite easy. Here is just a utility function that I've created just to print out the result. So this is just an helper function to have it here to print the result. And I'm using the namespace IPSC, APSC, that is a namespace where I have defined all of the classes that I've shown before. I'm here since I don't want to type all this long stuff. I'm saying that as fixed point iterator, here I'm using the fixed point iteration with vector, fixed point argument type double dot vector. That means that I'm choosing vector. That the iterator function is the one that is given by the fixed point iteration. The fixed point iterator defines a type called iterator function that is good and gets a type from the traits, but it's also in the fixed point iterator. So I grab from there, so I know what is the type for the iterator function. I create the iterator function, and now I need to fill the iterator function with something, right? At the moment it's an empty iterator function, there is nothing inside. And so I decided to have a simple iterator function with is a vector function of the dimension 2 that takes this lambda. This is a lambda expression. Huh? So it takes the lambda from here and return a vector double, okay? Because I know I'm choosing here vector, so I know that I have to return a vector double. And this vector double is initialized on the fly. This is a very nice stuff, because I'm just initializing the vector double with the first entry equal lambda sinus of x0 and the second entry cos of x0. So my iterator function has got two components, lambda sinus of x and cos x. If lambda is less than 1, the convergence, there is a fixed point, 0 and this number, and if the absolute value of lambda is strictly less than 1, that fixed point is stable, so it will converge to 0 and this number. The convergence will be slow if the absolute value of lambda is near to 1, at least for the non-accelerated version. If lambda is equal to 1, the fixed point, this fixed point exists but is unstable, and in general we do not converge. Okay? If lambda is greater than 1, we have two fixed points, one of which, the one with y here equals 0, is unstable, and the other is stable, and we converge to the stable one. Okay? You can try to change lambda and see what happens. Now I set lambda 0.9. Okay? So I have the fixed point. I create a fixed point iterator just passing my fixed point iteration function. I create the initial point, starting point, that has to be of argument type. Again, since I'm using vectors, I can use this very nice syntax. So the starting point is 5, 7. And with basic method, I just call print result, giving the value returning by iterate compute from starting point. So I will do the iteration, and I pass the result to print. Print, get the result with this very nice syntax. This is C++ 17. You can only use it if you compile with a C++ 17 compliant compiler that gets the struct returned by the method compute that contains the value, the iteration number, the last distance between two iterates, and if it has converged or not. This is just to print the result with a certain number of digits, and a printout. Just to make sure that also the version with eigen works, I use the same, exactly the same iterator function, but now using a fixed point iterator with eigen. Okay, so what I'm doing here, I'm creating another fixed point, phi2, of type iterator function 2. Iterator function 2 is the iterator function returned by fixed point iterator 2, which is, again, my fixed point iteration, fixed point argument type, eigen, this time. You see, now I want to use the eigen. And now the other change, I want to use as the second accelerator. So this is the case with acceleration, where I have also chosen, just to make things more complete and to test also the code, to use the eigen. Okay, I define phi. Now, since now I have the eigen, I cannot use the trick I've used before. I need to define an eigen vector of dimension 2 and set 0 and 1. This maybe is even clearer, less compact, but probably more understandable than what I did before. Res 0 is lambda for sinus, res 1 is cosinus, and I return res. Okay? Then all the rest is the same. I create an object of type fixed point iterator passing the iterator function. I create a starting point, the same starting point as before, but now is an eigen vector, so I have to define an eigenvector of dimension 2 and fill it with 5 and 7, and then again I call print result with a new iterator function. I should obtain the same result, maybe with less iteration, because now I'm using an accelerator. If the accelerator works, I'm gonna get the result with less iterations. Okay? Let's try to compile. You just type make. You get some warnings. Unfortunately, these warnings, you have to live with them. They are due to the fact that eigen use internally to indicate the index of a vector or of a type for the index of a vector or of a matrix a long int, while vectors, all the containers of the standard library to address an index, use this std size t stuff. That is the type used by vector to address the indexes, which is instead a long unsigned int. So they support also vectors with huge size. Okay? And so here I'm doing, inside the eigen, they're doing some comparison, and the compiler is giving me a warning. Look, you are a long unsigned int, and you are comparing with a long int. Are you sure that you're doing the right thing? Yes, I suppose that the eigen developers are doing the right thing. So I'm ignoring this warning. Okay. So the main has been created. It's called main fixed point, and I'm running it. As I see here, sorry, I don't know why this. Okay, I don't know why this is still here. Let's do like that. With the basic method, the fixed point iterator has not converged in 100 iterations. Remember that I haven't changed the number of iteration. I haven't changed the options. The last computed value, however, is not so bad. It should have been 0 and this number, more or less. And indeed, we are already near 0. So that means that we are nearly converged. With the second acceleration, instead, I was able to converge in 78 iterations. And indeed, this is morally 0. And this is indeed the number that gives the fixed point of the cosinus. You may try, if you do the cosinus of this number, this is given in radiant. If you do the cosinus, you get the same number, apart possibly the last digit. So just for fun, let's try to change lambda. Let's try to put, I said that if this lambda is smaller, the convergence will be faster. Let's see if I'm cheating or I'm saying the right thing. Let's compile. Let's run. Now both converge. With basic method, we converge in 40 iteration, and here is really 0. The fixed point converge in 20 iteration with this number. You see that there are some differences in the last digit, but this difference is clearly below the tolerance. Okay? So we don't get exactly the same result, but we obtain two results that are within the tolerance I have prescribed. So if you want, you can add the traits for the scalar type. Of course, you can use also scalar type by just using a vector of size 1 and interpret it as a scalar. But you may make a specialization, and it's not so complicated, for scalar type. If you do it, please give me the code so I can check it and eventually add it to the code for the example for the next students. Thank you.